Okay, in this section we're going to look at the laws of exponents, and we're just going to look at the laws for integer exponents, but later in calculus you'll use these where the exponents can be any real number, and in particular the exponents will be functions of a variable x, and quite often people have to review their rules of exponents in this new situation. So here's a chance to have a look at them for the exponents that we've defined so far, which is integer exponents. We have a to the m times a to the n is a to the m plus n. Pardon me. So if you multiply two powers of the same number, then you should add the powers. And here you see we have 3 to the 5 times 3 to the 10 equals 3 to the 15. This is true. It's very easy to see why it's true. If, for example, you have 3 squared times 3 to the 4, then this is equal to, by definition, 3 times 3 times 3 times 3 times 3 times 3. That's the 3 to the 4 part, and that's the 3 to the 2 part. But now this is just 3 multiplied by itself 6 times, so this is 3 to the 6. And that, of course, agrees with the rule here. A to the m times a to the n is a to the m plus n. And the proof is very similar to that. That's just an example, but the proof is very similar, except it involves a's and m's and n's as opposed to 3's and 2's and 6's. The second rule is that if you divide powers with the same base, then you subtract the exponents. So when dividing two powers of the same number, you subtract the exponents. So we have a to the m over a to the n is a to the m minus n. And you may already perform this automatically, just factoring. You might already call it factoring, and you may not go to the trouble of subtracting exponents here. So for example, 3 to the 5 over 3 to the 10 is 3 to the 5 minus 10, so it's 3 to the negative 5, or 1 over 3 to the 5. So you may actually write that as 3 to the 5 over 3 to the 10, and you may already consider that as an application of the reverse of rule 1 and just cancel the 3 to the 5's here, and that's 1 over 3 to the 5. Why is this rule true? Suppose I have 3 to the 2 over 3 to the 4. Why is that equal to 3 to the minus 2? Well, again, we can see this by expanding. We have 3 times 3 in the numerator, and 3 times 3 times 3 times 3 in the denominator. And now you can cancel two of these, and you get 1 over 3 squared, which is 3 to the minus 2, which is indeed 2 minus 4. Again, the general proof is very similar. It just involves a's and m's and n's instead of 3's and 2's and 4's. The next rule tells you how to deal with powers of powers. So this says a to the m to the n is a to the m times n. So when I raise a power of a to a new power, I multiply the powers, and I get a to the m times n. For example, 3 to the 5 to the 10 is 3 to the 50. Or, if you want to look at why it's true, a squared to the power of 3 is a times a to the power of 3 by definition, and that's a times a times a times a times a. That's a squared cubed. But now that's the same as a to the 6, which is indeed a to the 2 times 3, or 3 times 2. Notice that a to the 2 to the power of 3 is equal to a to the 2 times 3, which is a to the 3 times 2, which is a cubed squared. So we can actually switch the roles of the powers here, and that's often handy in calculations. If I have two bases, a and b, and I raise a times b to some exponent n, then I can distribute the exponent. So a times b to the n is a to the n times b to the n. What I'm saying is 3 times 2 to the 4 should be equal to 3 to the 4 times 2 to the 4. Why is it true? Well, this by definition is 3 times 2 times 3 times 2 times 3 times 2 times 3 times 2. And now I can rearrange things and put all of the 3's together and all of the 2's together. And now this is equal to 3 to the 4 times 2 to the 4. So that's really all this is saying. And in general, it works in general, and the proof is the same in general, except instead of 3's and 2's and 4's, you're using a's and b's and n's, and it means you can distribute exponents. If I have a fraction, a over b, and I raise it to the power of n, then I can distribute the exponent to the numerator and denominator. So for example, we have 2 over 3 to the power of 2 is equal to 2 over 3 times 2 over 3 by definition. And then using our rules of fractions, we have that is 2 times 2 over 3 times 3, and that's 2 squared over 3 squared, which is what the rule says it should be. Again, general proof is very similar, but instead of a particular fraction, you use a's and b's and n's to prove it. And the sixth rule isn't really a rule, it's just a rearrangement of rule 5. And it says a over b to the minus n is b to the n over a to the n. So this minus here means that you're talking about 1 over a over b to the n, and that's a fraction, that's a to the n over b to the n, so when you invert that fraction you get b to the n over a to the n. So for example, 1 over 2 over 3 to the 2, that's 2 over 3 to the minus 2, and that, according to our previous rule, is 1 over 2 to the 2 over 3 to the 2, and that's equal to 3 to the 2 over 2 to the 2. So again, this isn't really a rule you have to remember. If you can manipulate fractions and you know this rule, then, and you know the definition of a over b to the minus n, then you're set on this one. Proofs are not very difficult. Again, they're just generalizations of what I've shown you with particular fractions. Here's the generalization in the case of a to the m times a to the n, and in fact they're very easy. They just involve abstract variables a and m and n.